Welcome to the SSD project demonstration done by group 32. So this is the project we have selected. So this is a food ordering and delivery platform developed for the third year DS module. So here this is a fork project that we forked from the original project. So since this is a microservices project, we divided the services among the four group members in order to identify the vulnerabilities of the system. First, I will demonstrate the main two security vulnerabilities that I have identified. So, the first issue is the CSP header not set. So, without a CSV header, the browser doesn't know which scripts, styles, or frames it can trust. So, this exposes the application to attack like cross-site scripting and allowing the attackers to steal cookies, tokens, or even deface the site. So what I have done to avoid this is using a helmet middleware. So by using this, we enforce a strict CSP policy restricting resources to trust only the sources only. So the next security vulnerability I have identified is X powered by leak. So the second issue was that a server was leaking technology stack. So this reveals that the service was built with Express.js, which could help attackers target version specific vulnerabilities. So, in order to avoid that, I use a simple code snippet such as app disable x powered by. So, this disable the header in Express to hide the information. So, the next part I contributed for this project is implementation of OAuth. So here the user can proceed with registering with Google. Then they can pick an account. Then they can give access to the system to access the name, profile picture, and the email address. So that's it for my demonstration. Thank you.
So first I ran a SAP scan on an order service. SAP showed a vulnerability called missing anti-clickjacking header. This happens when the application doesn't include a header like X-frame options or a content security policy with frame ancestors. These headers tell the browser whether the site can be displayed inside an iframe. Without them, attackers can embed the size on a malicious page and trick users into clicking buttons without knowing it. This is called clickjacking. For example, a user might think they are clicking a normal button, but actually they could approve an order or change settings in the background. To fix this, I added Helmet middleware to the app. Helmet automatically sets security headers, including X-frame options. After adding Helmet and restarting the server, the headers now include X-frame options, same origin. This blocks the clickjacking attack. Um, next, I looked. Next, I looked for access control issues in order service. Customers should only see their own orders. Restaurant owners should only see orders from their own restaurant, and admins can see everything. Originally, the service was not checking properly. For example, when a customer requests order by user ID, the system just took the ID from the request. This means a customer could change the ID in the URL and see another user's orders. Um, Restaurant owners could do the same with restaurant IDs, only the admin routes were properly restricted. This is called broken access control. Uh, this vulnerability not flagged by ZAP. I found it manually by testing different user and restaurant IDs in the URL. To fix this, I added checks in the controller. Now customers can only access their own orders or cards. restaurant owners can only access orders for their own restaurant. Admin can access everything. If someone tries to access something they shouldn't, the service now return 403 error. For example, in get order by user ID, I added this code part. Uh, I did similar checks in other functions like get order by restaurant ID, update cart by cart ID, and delete order. After apply these changes, I tested manually and confirmed that customers and restaurant owners cannot access data outside their scope, while admins still have full access. This closes the broken access control vulnerability.
So I have found these vulnerabilities in the API gateways content. So the first one is a CSP wildcard directive that I have focused on. I have found that our API gateways contain security procedures using wildcard directives. This means the browser could load scripts, styles, or frames from anywhere, even malicious domains. That defeats the purpose of CSP, which is meant to control exactly where resources can come from. If exploited, attackers could inject JavaScript, steal data, or perform clickjacking. So I have fixed this by configuring a helmet with a strict CSP, only allowing resources from trusted domains like Sales, Google Fonts, and our CDN. So this is the code snippet I have added to fix this vulnerability. So the second vulnerability I have found is the cross-domain misconfiguration. Initially, cause was too permissive; it allowed any origin. That is dangerous because malicious sites could send requests to our API and potentially steal token or perform unauthorized actions. I secured it by restricting requests only to trusted domains and controlling methods, headers, and credentials. This is the code snippet I have added to fix this. Additionally, I hardened the gateway further by adding route handlers for robot txt and sitemap xml, so sensitive endpoints won't be indexed or exposed to crawlers. This is the code I have added to fix that one also. So these are the two vulnerabilities that I have fixed in the API gateways content.
During my security testing, I identified two key vulnerabilities in our service. The first vulnerability is that the application did not include the X-content type option header. Without this header, some browsers may try to guess the content type of a response, a behavior known as MIME sniffing. This can allow attackers to trick the browser into executing malicious files as scripts, which increase the risk of cross-site scripting attacks. To fix this issue, I add the helmet middleware to the application, which automatically set the header to none if this ensures that the browser only interrupts content according to its declared type, removing the risk of MIME sniffing. The second vulnerability was related to the Content Security Policy or CSP. The scan reported that the CSP configuration was missing important directives with no safe fallback. When these directives are not defined, browsers may allow resources to load from any source, which exposes the application to cross-site scripting, malicious code injection, and other attacks. To resolve this, I updated the CSP configuration to explicitly define trusted sources of scripts, styles, and images. After applying this change, the HTTP response now include the complete and restrictive CSP policy. A- After both fixes were applied and the services restarted, I reran the sub scan and it confirmed that the vulnerabilities were solved.